shows where we're at. Today we're going to take a look at something called related rates. And if you understood 11.6 implicit differentiation well, today will be just more of the same. If you didn't, today might help in understanding that one as well, because they're connected. I would say today's is a little cleaner in a sense, and maybe a little bit more understandable, but they help with the connection. So we'll kind of make the connection between those two. After spring break, we return to, again, it's an application, so no new methods, but just taking what we've already learned, applying it to certain problems. We'll actually have a formula that we will use. I'll see whether it's provided on the exam. I'm of the opinion that I would provide it for you maybe on the board if it's not on the exam, but it's just because it is a formula, you have to kind of remember. I don't remember what it is right now, but I just remember there's this formula with a derivative in it, and it helps you get it. So we'll go over that and move forward. Any questions or comments or concerns before we move into today's content? Okay. So let me go ahead and open up here. The slideshow. So this is applications of the derivative. Nothing really new. And what's going on here is we're going to have our x and y in there, two variables, but there's going to be a variable we don't see, and that's time. Okay, so there's sort of this, when we're thinking, we're dealing with sort of a three-dimensional thing, or at least three-variable thing, but one of the variables just doesn't show up. So but the questions will talk about change over time, and so time is involved, but it's not a variable that you necessarily see. But x and y, their change is happening over time. So what do you think if we have, let's see here, before I get to the next slide that puts it all out. If we had x changing over time, what would be its derivative? How would we write its derivative? Thinking of when we did implicit derivatives. It'd be 1. Yeah, the derivative of x is 1. What would well, instead of going on the fishing trip, it would be dx changing with respect to time. Okay, so yeah, so the derivative of x is 1, but we have this thing, because it's changing in respect to time, it's not changing in respect to y or anything else. Changing in respect to time, we'd say it's 1 dx dy, or dx dt. Likewise, when we see the variable y, if it's changing over time, what would be its derivative? dy over dt, exactly. So this is a thing, and then you go, well, where's dt? I don't see it. Well, yeah, time is like that. You don't see it. It just happens, right? So that's the idea, is that there's the change of y is happening over time, but there is oftentimes not a variable with time. Sometimes it will occur. Okay, there's actually a factor that over time something's changing, but most of the time when we're dealing with time, it's just a dx dt, dy dt, and we'll see there, whatever the variable is, it's that variable over dt. It's changing over time. So that's what they start off with. If some quantity q, whatever q is, q for quantity, as it changes over time, they give us the answer here, that's dq over dt, just like dx over dt. So it's, and we'll use it like with implicit derivatives. We just take the derivative of the variable like we've been doing with x. We use our derivative rules like we've been doing, but we just put this marker that this is the derivative of, in this case, dq with respect to time. Okay, it's just this marker thing. So we're going to see how that works. And actually, someone looking over 11.4, I got realizing it had some of these kind of things in there that I hadn't realized were there. So this will actually probably unlock a few other things that you might not have gotten through yet. If we're talking about area and area size of something, and we'll talk about circular areas and volumes, whatever, but if area is changing over time, then its derivative is dA dt, derivative of area over time. Okay, so we'll see that. And oftentimes, like I said, with a circle, what we can measure oftentimes is maybe the radius, how the radius is changing with time. But as the radius changes, so does the area, but the area changes differently than the radius. So we got two rates going on, but they're related, because as the radius gets bigger, the area gets bigger, right? So we're gonna see how this all fits out. When we go through this, you're kind of gonna, it's gonna get into your knowledge of geometry, because that's, most of these are physical type things. So a little bit, not too much. The good news is most of the time they'll give us the formulas. Area of a circle though is pi r squared, so that's a fairly simple one. We're gonna do it with also with like a balloon, a sphere. They're gonna give us that formula because it's not too bad, but who carries that around in their mind of, you know, what's the volume of a balloon? But we're gonna use those things. And again, we've got two different variables, r and v for volume, or r for radius and a for area, but they're both changing over time. So there's this third variable in there. So we're going to be seeing, we're using this implicit differentiation with this sort of marker, okay? And as r changes over time, as they say, we're going to do dr dt. And so we're going to come up with equations that have, sometimes the variable r still there, there's a variable there. We're going to have two different rates, right? dA dt, dr dt. And to be able to solve for one of those rates, we need to know what the other rate is. Because as that rate changes, the other rate changes. So part of the problem, the difficulties with these on the abstract level is there's multiple things going on. There's multiple variables. There's more than one rate of thing that's happening. There's the size of the radius that's changing. There's the amount of the area that's changing. So those are both happening. And as one changes, the other changes. So it's kind of like this moving, what they call like a moving target. Everything's in motion. So what we do is we have to pinpoint a particular instant in time. At this time, that all these things are fixed. So how is this one thing changing? So we'll get it down that we'll look at it that way. Okay. So I'm going to go through this. The PowerPoint actually had this later on. They gave an example first, but I'm going to do this first, and then we'll go through an example together and see how it works. So most of this is, again, as far as calculus, it's nothing new. We did it before. This is more about the problem-solving process of getting it set up, and then you'll see it's actually going to be simpler than what we did in 11.6. It's going to be simpler than what we did with implicit derivatives. So that's why it starts to make more sense. But the hard part is setting up the problem sometimes. So we're going to have multiple changing quantities. We have to read through that. We have to restate the problem in terms of what rates we're looking for, what formulas there might be. So again, if we're talking about the area of a circle, pi r squared, right? So we're going to just have to pull those out. If we're talking about triangles, which we'll look at a couple examples. So most of that is, basically we've got the stuff here. We'll look at a few examples and go through those. And sort of set up an equation. Then we have to, oftentimes we're drawing a picture because it's a physical study, so that helps us set everything up. Get our equations set up. If we need to, once from those equations we can take the derivative with respect to time, right? So we're using that implicit derivative. And then somewhere along the line in the question, they've given us some of the details. We substitute the details we've been given. Maybe when the radius is 5 inches, the radius is changing at 2 inches per second or something. We've got some information. We've been given one of the rates. We've been given one of the variables, and we're able to solve for the missing one. So that's all the moving pieces. Okay. So, and that's basically the lesson for today. What we'll do is I've got 3 or 4 examples we'll work through. We'll see how it works. If you want some more, we can dig into the homework and look at a few other examples as we go. So here's the first one. We've got a radius of a circle. the radius is increasing at a rate of 10 centimeters per second. So what is this? What do we call this in calculus? What do we call a rate? It's a derivative. That's going to be our derivative. Excellent. And since it's a radius, we're going to see this is a dr dt, right? Because the radius is changing in respect to time. That's that hidden thing over the time. So we'll see that's, so that's just kind of, okay, we got a rate here. And then the question, how fast is the area? And again, fast is a rate. So that's going to be a derivative actually of the area, right? That's what we're looking for, a rate of the area increasing at the instant when the radius has reached 5 centimeters. Okay, so this is what they gave us. So we draw a picture, okay? Got a radius of a circle, so here's my circle. Here's my radius. The radius is increasing, so maybe I just show that it's going to get bigger. The radius is getting bigger, and I'll say that's a rate, dr dt equals 10 centimeters per second. Okay, so that's what's happening. I can say, okay, that's happening. The question is how fast is the area increasing? So the question, how is the area changing, dA dt, when the radius has reached 5 centimeters. So we're at 5 centimeters, and again, we're looking in terms of instantaneous rate of change. Where's it going from there? So where do we start? What's an equation we might be able to work with? Five times. Oh, pi. Where are you getting the 10 though? But what is this 10? Is this a radius? It's how the radius is changing, right? It's how the radius is changing. So what we want to do first is we want to set it up with all variables first. So we know that area is equal to pi r squared. So that's our first step, is what describes the change, the area of a circle, pi r squared. Area equals pi r squared. We don't have any rates in that equation, do we? But we've got some rates information up here. So what we do is we take the derivative, and the question is about a rate. It's not about the area. It's about how the area is changing, so it's about a rate. So if we want things to be changing, that's where the derivative comes in. So we're going to take the derivative of both sides. So we take the derivative of area with respect to time. And again, the only thing that you really see is, time is involved here, the rates in time. And that's going to be equal to, now remember, pi is not a variable, it is a number, 3.14, blah, blah, going on. So we just treat that symbol as a constant multiplier. When we take its derivative, it just sort of stays there. So we want to take the derivative of the right-hand side, and what do we end up getting when we take the derivative of the right-hand side? Excellent. The 2 comes down in front, we subtract 1, so we end up with 2 pi r to the first power. That's not everything. What else do we get? dr dt. We get the marker that we took the derivative. So this comes from implicit derivatives. Okay, now, so that's the main, this is the hard part of the whole thing. You got to see the picture, come up with an equation that describes a situation in static, right? This is a static equation we came up with. And then make it a changing equation by taking its derivative. And we're going to get, in all these cases, we'll get two rates on this, right? 2 derivatives, a dA dt, dr dt. Now we come back up here and we can start plugging in things that we know. We see a 10 and we see a 5. Now we got to figure out, where do those numbers go? How about that 10? What is that 10? It's dr dt, because it's the radius of a circle is increasing at a rate. It's a rate. So as we said, this is dr dt. So we come down here, dr dt, hey, That's now just the number 10. Nice and smooth, right? It's not the RDT anymore, it's 10 in this particular instant. What else do we know is happening at this particular instant? Excellent. At this particular instant, the radius is 5. R is 5. That's what R equals 5. So we come down here, we see an R, we can put a 5. And isn't this nice now? We really have an expression with all numbers. That's all what we're looking for mathematically. We've solved our problems, right? Because there's only really one variable thing left, or one unknown, and that's dA dt. But the cool part is that's what we're supposed to find, right? That's the question. How fast is the area changing? So we just now need to do the arithmetic. 5 times 10 is 50, times 2 is 100. So we could say, not 110, 100 pi. So the area is changing at 100 pi. I guess we could use units here, right? Since it's going to be area, right? This was radius, this is centimeters per second, this is going to be centimeters squared per second. Okay. I think in the homework we just need the number, but you want to keep track that this is a rate, so this is centimeters per second, and since this is area, it's got to be centimeters squared per second. So that's what's happening is, as the radius is, so we're at 5, we know in the next second that radius is going to get 10 bigger, so it's going to be at 15 in the next second. What's the area going to be? It's going to be 100 pi bigger. And so that's what's happening each second. The area will get 100 pi bigger than the previous second. The radius will get 10 centimeters bigger than the previous second, over that second. So we got those two things happening. Make sense? And again, this is math of an oil spill. We know how fast the oil is coming off of the ship that's hit the rocks. So we know how fast that radius is growing. It tells us how fast the area is getting. Then we know, okay, we got to get these booms out so that that circle of oil doesn't grow any bigger. All those kind of things. How much time, and that's what they use for it. They're using calculus. Okay, and they'll even use it more complicated because the calculus is that rate doesn't always stay the same, right? Because it's how much pressure it is pushing out. So you got sometimes it speeds up, sometimes it slows down. All that kind of stuff. But that's what we're doing. Okay, so this is the first example. I did it all on one page. I left, this is from the textbook. So this, if you want to read through this, this is the textbook solving it, doing basically the same thing we did, right? The RDT, we set that up, but there's all the words here, and this, you have access to this through Canvas. So if you want to kind of read in more detail, they're saying, yeah, remember we said R equals 5. I went ahead and I start with the equation first, okay? Because I know it's going to be circle. I know the equation of circle. Go from there. And again, they talk it out. They finally got to the equation here, right? They're going to take the derivative of both sides so that they can get the ADT. So this is where we really started. We got here pretty quick. But again, there's all the words there that sometimes could be helpful. We substituted in our values, so this is kind of it in slow motion. We put our 5 and our 10, and they did this. Now they came up with 314 centimeters squared because what they did is they took pi as 3.14. 3.14 times 100 is 314. So I left it as 100 pi, which a lot of times we do. Again, engineers, because maybe you want more accuracy, so you have all the decimals there, but whatever they want. If they may want the 314 centimeters per second. Make sense? Okay. So we're going to see a couple different situations, because that's the process is going to be basically the same. Once we have our equation, we just do the derivative of both sides, and these equations actually are going to be fairly simple. They won't be anything more than maybe squared or cubed. They're not too funky because it comes from geometry. and then we go, move forward. So yeah, they went that route. So now let's go to another step, and this, again, may seem like a different place because, again, it's going to bring us back to some geometry that we may not have been looking at for a while. Maybe it was 7th grade the last time we talked about triangles. I don't know. Maybe it was last week. But Jane is at the top of a 5-foot ladder. When it starts to slide down the wall at a rate of 3 feet per minute, okay, 3 feet, so it's not too fast. It wasn't 3 feet per second, so Jane's not in too much trouble. Jack is standing on the ground behind her. How fast is the base of the ladder moving when it hits him if Jane is 4 feet from the ground at that instant? Okay, so again, we got to draw a picture. Okay, so what we know is there's this wall, there's a floor, and then there's a ladder leaning against the wall. And the ladder, we're told, is a 5-foot ladder, so we know that's fixed, right? That ladder's not going to change size. It's just 5 feet. What else do we know? It's a moving ladder. It's starting to slide down the wall. So it's sliding down, but just be careful. This rate is not a fixed quantity. It's a derivative, right? Anytime we have a rate, it's a derivative. So we know it's going down at 3 feet per minute. We'll kind of put it out there. That's a rate. So we have to kind of set some things up, and then, but we know that with a fixed ladder, if the top's sliding down, the bottom has to slide out too. If you've ever, so part of this is this has to be moving out this way. So we have to invent some variables here, and I'm going to ask for your help on this. We may do something different than what the textbook. Again, we're going to, just like this, it's got the textbook put a whole 3 pages of explanation, and they came up with some variables, but I just want to see what we come up with. What would you like to call, so at some point, this is a static thing, so we've got the 5-foot ladder. Recognize we've got a triangle here, right? So that's what we're going to probably, what comes to mind with a right triangle as far as formulas? Got area of a triangle, 1/2 the base times height. Is that going to help us here? No, there's nothing about area, so we can throw that out there. There's how one side is changing of a triangle and the other side of a triangle is changing, right? What do you remember? What kind of formula do you remember gives you sides of triangles, of right triangles? The Greek guy. A squared plus b squared equals, yeah, Pythagorean theorem. Okay, so yes, there's this a squared plus b squared equals c squared. And what does the c variable refer to? Hypotenuse, right? So could we just call this side A and this side B, right? And this would be side C. Side C doesn't change, it's 5 feet, but obviously B and A and B will change. I think you could use other variables if you want, but this is what we're going to use. Pythagorean theorem. Okay, we know this relationship here. And we just defined A to be the height. So we've got an equation that has the relationship of the two legs of the triangle to the fixed side, the hypotenuse. What should we do? Plug in the numbers we have. What do we have? We've got 5 for C. Excellent. Let's go ahead and do that. Because more numbers, we feel maybe a little more comfortable. So then we know that A squared plus B squared has to be equal to 25. I'll just go, so C squared, 5 squared is 25. Okay. What else do we know? We know a rate, but I don't see any rates in here yet. We do know this 4 feet, but I'll be careful about this. This is at particular instant. We don't want to plug that in just yet. Okay. And there's a reason why we don't, because what happens when we take the derivative of a number? It becomes zero. And the rate might not be zero, but if we turn it to a number and then we take its derivative, it's zero, we'll never get its rate. So what we want to do is this is okay, this 5 is never going to change, and there's really no rate involved with it, so we were okay here, but what we're going to do next is take the derivative, and then we'll plug in the rest of the stuff we know. So, and if we wanted to at the beginning, I guess we could have, but yeah, it's kind of nice. So what's the derivative of a squared?
2a.
And?
2b.
dA dt. Good. So remember, there's always this, because we're taking the derivative with respect to time. We have to have that marker there, and we're going to see that becomes pretty important. And then you're right, b squared, we take its derivative, it's going to be 2b. So the 2 comes down, subtract 1, so it's 2b to the first power. But there's also the marker dB dt. So that's how b is changing with time. And that's actually what we're going to be looking for, right? Because we want to know how, what's his name? Jack. How, when the ladder hits him, how fast is that ladder going? That's this part here. That's dB dt, right? The rate. And then derivative of 25, 0. So that's why it's good to go ahead and put that in, because that's not going to change. It doesn't change that rate. Okay. Now what should we do? Too many variables. But we know some of this, right? What is this 3 feet per minute? It's our dA dt. What direction is that going? It's going down, so it's negative, because it's that height is actually changing, is getting smaller, right? It's going to become 0 when it hits the ground. So maybe we should have put a negative on it, but that's our dA dt, how it goes down the road. Okay, so there's a minus 3, so that's dA dt. Let's see, what else do we know? How fast is the base of the ladder moving when it hits him if Jane is 4 feet from the ground? So Jane is 4 feet from, so that means she's at the top of the ladder. And I guess at the very top, although they tell you don't stand on the top, right? This is a security or safety warning, but she must be standing on the top. So she's at 4 feet, so that means, what about A? A is 4 at this instant. Good. So that we can put in now. Again, if we put it in earlier, we wouldn't have had a place to put the rate, because it would have gone away. So it's kind of, that's what I used to do, and then I go, oh wait, what do I do with the rate? Because this was 0, right? So we put the 4 in for A, and then what, now we got B, and we got dB dt equals 0, but so this gives us 2 variables. We got a problem here. How could we solve it? So we've got B, which is at this point still an unknown. dB dt is an unknown. Is there something we could do where we could get knowledge of one or the other? Exactly. So we come back up to here. We could actually, so this is, since this is a situation when A is 4, we could figure out what B is at that instant as well. So sometimes you go back to that original equation. So we're going to come back up here, and we're going to say, oh yeah, if A is 4, so we get A squared plus B squared equals 25. So that's 4 squared is 16. Subtract 16 from both sides, right? So that we get B squared. 25 minus 16 is 9. So if we take the square root of both sides, b must be 3. Now we do get a plus or minus, but a distance of -3 makes no sense, so we say we use 3. So when a is 4, b has to be 3. And so we're going to see at that instant, and so that takes another variable out of here. And what we're left with is what the question's asking, how fast is, and that's what this rate is, dB dt. Okay, so now we've got everything is numbers except for one thing, and that one thing that's still sort of an unknown, that's what the question's asking us. So we're in good shape. Arithmetic, a little bit of algebra, and we're done. 2 times 4 is 8, times 3 is 24. So there's -24. 2 times 3 is 6. dB dt equals 0. We add 24 to both sides. So we get 6 dB dt, run out of room, equals 24. Divide both sides by 6, right? 24 divided by 6 is 4, 5, 6, 3, forget 4, it's 4. Okay. Like I told you, it's arithmetic and algebra. That's the hardest part of calculus. You're so busy doing all this stuff that you forget what 2 plus 2 is. But that's what we have calculators for, right? It's 4. So it's moving at 4 feet per minute. It's not incredibly fast, but 4 feet per minute. It's only a 5-foot ladder. It's going to be down pretty quick, but right. Does that make sense of how we went about that? So it's a sort of a problem-solving thing. Is you got to get your formula. Make sure you take, plug in the things that are fixed that you know of, and then but take the derivative early enough so that sometimes if you plug in too much and then you got a number too early, you take its derivative, you get 0, but you really need, it's really something that could have a rate to it. The thing we knew about it was okay to plug in the 5 is the length of the ladder was not going to change. The only two things changing is how far up the wall it is and how far down the floor it is. So there's two things changing, but the length of the ladder is not going to change. So we knew that was going to be fixed. We put that in early. But we also had to return to this equation because when we did everything, we still had two variables. And that's the thing is you'll learn in math, we can't solve anything until we have only one variable. If we still have two variables, we gotta get it down. And so we sometimes can go back. Okay. And then this is the textbook solution. So again, if you wanted to, if you want to read through it, because sometimes that helps. This is everything we talked about in maybe a more direct way than I did, but sometimes you need to kind of have it a little sloppy going back and forth. But they used h for height. We used a because that came out of our natural a squared plus b squared equals c squared, but we could have used h for height, and they still use b for the base distance on the floor. Rephrasing it, they do know that the ladder was going down, so that was a -3 rate. So they picked that up early. We knew it was 3 feet, but we picked it up as we got into it. And then they rewrite it, so the change of the height is 3. Find how the floor is changing when the height is 4. They draw the picture now. We drew it a little earlier. They use this Pythagorean theorem, h squared plus b squared equals 25. So that's kind of, we did a and b. They took the derivative just like we did. Okay, started substituting things in, and again they did kind of like we did. They said, oh wait, we're going to have too much in here, we're going to have to solve for b. So they kind of went back to their formula just like we did, plugged in the 4 and solved for b, and they were able to find out that well, see, they got to this place, but they were able to find that b has to be 3. then they go ahead and plug that into the equation. They already took care of this part, it's negative 24, 2, 3, and then kind of kept along, solved 24 divided by 6, and hopefully they got 4, just like we did. Okay, so again, same thing we did, but one was kind of an actively getting us to think through it. This is kind of a textbook, nice, all complete. Yes?
Like the Pythagorean theorem part, what if we took the derivative before we plugged in the 5c?
Okay. Then we would have had to deal with, so actually, let's kind of pretend let's talk about that here. So what if we did a squared plus b squared equals c squared, and we just, okay, let's take our derivative here. So we would get 2a dA dt plus 2b dB dt, and then we would have said, oh, c is going to be 2c dc dt. This is a place we'd have to, okay, so how is c, which is the length of the ladder, how is that going to change over time? What is dc dt? Is the ladder changing over time? Is the length of the ladder going to change? It's a constant. So that would mean that its derivative would be a constant. So it would be 0, and so, oh, whatever 2c is, it's going to be 0. So we got the 0 there. So, but you're right, it's sometimes we're not sure, should I take the derivative at the very beginning, or should I do it later? If we do it, then we just have to, we're stuck with this, okay, what really is dc dt? Because they didn't tell us, oh, but a ladder's not going to change, so it's got to be 0, so it'll work out the same way. Okay, so then we still get that this whole side has to be 0. Okay, so we're about the same place. But, and that's really what I was saying, is the ladder's not going to change, so its derivative's going to be 0 anyway. Let me go ahead and plug it in, and I get 0. But notice if I would have plugged in because we knew a, if I plugged it in here, okay, and then when I took its derivative, I would have got 0. This whole thing would have just been 0, and I would have been stuck, and I go in circles. That's the way I used to do it. I mean, I remember learning doing this, and that's what I would do it too soon. Go to my professor's office hours, and he'd explain this, and so it's kind of, you learn as you go. Okay, and we don't always know. We try something, but then sometimes that was the hardest thing to learn, is when I tried something that wasn't quite right, what should I do to get out of that? How do I get unstuck? And that's why I try to do sort of a problem-solving approach through it. And if we get stuck, and try it. And sometimes it works. A different method will work, but other times it doesn't seem to work. But you have to kind of get into the problem. And yeah, if you look at the textbook, you thought, okay, I'll just do it their way, but you sometimes don't deal with those harder parts of, well, what if I took the derivative at the beginning? So now, this was all that's in the PowerPoint. So I took a few from the homework, and what you'll see is in the homework you'll have exactly the same problem, but you might have a different number here instead of 15. So the way we work through this, we'll give you a model for going through that. You'll just have a different number to plug in at a particular point, but there's a couple different ones with this spherical thing, so I thought, let's go ahead and do this. They do give you the volume formula, which is nice. On the test, at least when I taught this before, they have had a question similar to this, volume of a spherical item. They give you the formula, so you're not expected to memorize that. Okay, so a rather flimsy spherical balloon is designed to pop at the instant its radius reached 3 centimeters. So that's not very, so it's a smaller balloon. Anyway, 3 centimeters is going to pop. Assuming the balloon is filled with helium at a rate of 15 cubic centimeters per second. So this is a rate. What is 15 cubic centimeters? What kind of a measurement is that? Cubic volume. So it's the space inside the balloon. So we know the volume, or we know, actually, we know the rate the volume is changing. Okay, that's something. Calculate how fast the radius is growing at the instant it pops. Okay, so when does it pop? When the radius is 3 centimeters. So we have to kind of go back and forth on these things. So again, we start with the formula. Volume equals 4/3 pi r cubed. No rates in there, right? That's a static situation. But since we've got rates, one of the rates we're given here, we are given that it's at 3, but again, we don't want to do it too soon because the radius is changing. We need that derivative. So if we plugged it in now, we'd get a 0 when we took a derivative. We want to get the derivative first so that we can have that rate. Okay, so we take the derivative of both sides. Derivative of v is d1 dv dt. Okay, that's the, so it's just like it's a single variable, so derivative of it is 1, but I put the marker. I took the derivative of the what did I say? Derivative of volume with respect to time. Okay, we got our 4/3 here, so I'll go ahead and write that. When I take this derivative, and pi stays pi, the 3 comes down, so we're gonna, again, in taking the derivative, 3 is gonna come in front here, multiply. I'm gonna subtract 1 from this, so we're going to get r to the 2nd power, and this was dr dt. Okay, we've got a 3 times 4/3, 3 and 3. 3 divided by 3 is 1, so those can cancel. So my sort of simplified formula is just dv dt is equal to 4 pi r squared dr dt. Now this is a dynamic situation, things are changing, but what we want to know is what does a situation, what's the snapshot of this picture when that balloon pops, right? So at that snapshot, what do we know? We know the radius. The radius has to be 3 centimeters at this instant. Okay, so we can plug that in. We also know the rate that the volume is changing. We know the derivative of the volume. We know dv dt. So this 15 is dv dt. So we can start plugging that stuff in. So we can go 15 equals 4 pi. R is 3 centimeters. dr dt. Not dt dt, dr dt. Okay. That's the one thing we don't know, and that's what the question's asking us to find out. So we've got all numbers. 3 squared is 9. 9 times 4 is 36. 36 pi equals 15 dr dt. So we'll put this up here. Dr dt. So we divide both sides by 36 pi. So we get 15 divided by 36 pi. That's our answer. They want it to 2 decimal places, so they actually want us to plug it in a calculator. And I would use the pi button. So 15 divided by 36. Let's see, where's the pi button? There's the pi button. 36 pi. And I get 2 decimal places, 0.1326, so 13 will do. And that's going to be in units, it's a radius, right? This is how the radius is changing with respect to time. So radius is a linear unit, so that's going to be centimeters per, what is our time unit here? Second, yeah, so with this rate, it's per second, so our time unit's going to be the same, 0.313 centimeters per second. So that's how the radius was changing right when it popped. Now it's not going to change at all because it's popped, right? But that was the speed of the radius at that instant. And those are things we can measure. You're filling a balloon because there's a pressure. You know how much volume you're putting into this thing. So those are things we can measure. We could then figure out how fast things are changing. And of course, we probably want to know before it popped or something because maybe it's going to bump into something. So then you could, that's what we could use all this for, is how fast reaction time we're going to need for something, or how fast a reaction is going to happen when it gets to a certain then it hits something else. And all those things can be solved with these types of problems, related rates. Is that pretty straightforward? Okay, so the calculus part is not complicated. There's fairly simple derivatives that we're taking, but setting up the problem, knowing when to plug things in, and that we've got two variables that we're taking the derivative of at the same time. We've got two different rates. There's a lot of moving parts. The key part is getting the controlling part. To me is always, it starts with a variable, a formula where we have our two variables, take its derivative. They'll give us one of the rates, hopefully some way to get to one of the variables, and then we go from there. Want to see one more? We still got lots of time, so. Okay, here's a business one. Okay. So we're given a formula. This is the average cost function for the weekly manufacture of retro portable CD player. So again, the reason we know we're dealing with time is because they're telling us that this is a time dependent formula. It's per week. So average cost to produce a portable CD player. Do they still make CDs anyway? They do? I thought they stopped for a while, but I don't know. Everything's live streaming now, but yeah, they're still, okay. They still make them. So this would give us our average cost. And again, average is, if you make 500, the cost per unit is so much. So these are dollars per player. We've got this formula. And that's what that little bar means, is that's an average cost. Where X is the number of CD players manufactured that week. Weekly production is currently 4,000 players and is increasing at a rate of 400 players per week. So what is this 400 players per week? What type of a number is it? So rate, it's number of players. Remember, X is the number of players. So this is really going to be a derivative. It's going to be dx dt. This is how many players we currently have, so that's going to be X. X equals 4,000. So you can kind of do this in either order, but whenever you see a rate, you know that's going to be a derivative. When you see a number, this is the number of players, okay, that's going to be it. So what's the first sort of step to take? We've got a equation, but it's got no rates in here, right? Get the rates in it by taking derivatives. So this is a cost function. So on the left-hand side, you just have to know that, well, we'll take the derivative. So it's dc dt, the derivative of cost. So really, again, we think back, this is actually, well, since it's average cost, it's not quite a marginal, but sort of that. So we get dc dt, which is how the cost is changing. We take the derivative, so we've got 100,000 x to the minus 1. So remember that this exponent is going to come down in front. So we'll have negative 1 times 100,000, so negative 100,000. x to what's the exponent up here?
Negative 2.
-2. We're subtracting 1 from it, so -1 minus 1 is -2. Very good. And what else do we need here? We took a derivative with respect to time. We need a dx dt. Take the derivative of 20, we get 0. That's nice with constant. Take the derivative of 0.0006x, and we get 6, but we took a derivative, so there's a dx dt. Okay. Now when we have two of them, two dx dt's, what we can do is we can factor them out, or we could plug them in, whichever you want, however you want to deal with them. But I might say, oh, there's a dx dt, there's a dx dt. Let me factor them to the back. Let me rewrite this as minus 100,000 x to the minus 2 plus 0.0006 dx dt, and that's equal to dc dt. Okay. Now what can we do? We can plug in the stuff we know. So what is happening to the average cost? Actually, I guess I should, this is not just, this is the derivative of the average cost. So that's what we want to know. To figure that out, we're going to have to plug in what we know. So we know there's 4,000 players, that's an x, so this x becomes 4,000. So minus 100,000, 4,000 to the minus 2, plus 0.0006, which might not seem important, but maybe it is. And then what do we know about dx dt? It's 400. At this point it's changing 400, so it's 400. So we got all numbers. We've got just one unknown, the average, the derivative of the average, the rate of the average cost, which is what we want, this is the question. So we plug all this in our calculator, and so minus 100,000 times 4,000 raised to the -2 power plus 0.0006. I better put a parentheses around that, and then I'm going to multiply the whole thing by 100, or by 400 times 400. When I do that, let me write that over here, dc dt. See if I did that right. 1, 2, 3. There's 4,000 players. The rate of increase is 400 players. It's increasing, so that's positive. Coming up with a different oh no, I guess that's the same answer I came up with. Yeah, and I checked it. I did this earlier just so but I thought it was a different answer. Anyway, I come up with negative 2.26. And what is that? Well, we go, it's cost, right? It's how cost is changing, so that would be $2.26 per player. The average cost is reducing by $2.26 per player. So these are negative dollars per player. And again, for the homework, you don't have to plug that part in. But it's always good to kind of try to go back, what kind of a rate do I have? That's a dollars, cost of in dollars per player. So that's kind of good. If I do that, average cost is going down, so I can make them cheaper. Hopefully I can sell them at the same price, all that kind of stuff. Does that make sense? Any questions? So this is one from the homework. The previous one was from the homework. There's a couple ladder type problems, but they got 35-foot ladders instead of 5-foot ladders. So, but the setup's going to be same. Sometimes they want the rate how fast it's coming down. Sometimes they give you the rate of how it's going on the floor. But again, the setup's fine. There's a couple volume problems with a balloon, a spherical balloon or basketball or something. So that goes on. You got that. There's a couple circles, area of circle changing. But just remember, it's the hardest part is that you're taking a derivative with respect to time, and there's no time variable in there, but it's the whole thing is changing over time. All right. Good shape. Again, we got to practice our derivatives and taking them. As you get through this stuff, it's good to start going back and maybe working through that practice test, or that I don't know if they call it a practice test. What do they call it? A review. Down here, yeah, these review modules. There's some. They used to have a WebAssign review. I don't think there's not one anymore. They stopped doing that. But there's videos on with the screenshots, and I worked through the problems. There's a study guide here. Take a look at that. And again, there's solutions, answers worked out as those help you. When I get a new study guide, which I probably will be sometime after spring break, but when I get it, I'll go ahead and post it, and when I get the test, I'll make sure we're focused and we know kind of which ones we need to focus on. Okay, but right now, just kind of keep on moving forward. Let me know if you have any questions. I'll try to take a break too. It's hard to, but take a break, refresh, move forward, and get caught up all at the same time, right? So, all right. Thank you all. Have a great week off, and see you when we all get back.